Here are the answers to exam 1. First problem, you were supposed to find the composition f circle g of x and then find its domain. So if you remember that f circle g is f of g of x, then you can just replace g of x by what it's equal to. And in this case, that's 3x minus 2. So you're taking f of 3x minus 2, which means take 3x minus 2 and stuff it in wherever you see x in the formula for f. So that means instead of the square root of x plus 5, you're going to get the square root of 3x minus 2 plus 5. And that, of course, simplifies, and you should. This is the square root of 3x plus 3. So that is the formula for f circle g of x. And then the domain is all the numbers that you can legally plug in here. And the only ones that you can't plug in are where the stuff under the radical would be negative. So for the domain, you want the stuff under the radical to not be negative. Well, that means greater than or equal to 0. 0 makes sense under the radical. So 3x plus 3 just has to be bigger than or equal to 0. That's the same as 3x bigger than or equal to negative 3, or x bigger than or equal to negative 1. And so that would be the domain. Of course, you could say negative 1 out to infinity, like that if you prefer. Okay, that's number 1. Number 2, you're supposed to find f inverse, where f of x, or y, is 3 plus square root of 2 plus x. Well, the algorithm that the book gave us for this was to switch x and y, and then solve the resulting equation for y. So first thing you do is subtract 3 from both sides, and you get a radical on the right. Square both sides, so that's going to give you 2 plus y, and x minus 3 squared. And then subtract 2 from both sides, and so your inverse, f inverse, which is y, is going to be x minus 3 squared minus 2. And this is an exam. There's no reason on earth to have to multiply out x minus 3 squared. Just leave it that way. There's not a single reason to multiply that out. Okay, now, one of the problems that caused the most difficulty was this one where you had this weird function that's defined in pieces. And if you look carefully, the first part is 2x, which everybody should recognize as a line of slope 2. But it's only on the domain where x is less than negative 3. The second part of this function is a line of slope 1, y-intercept minus 3, but that's only in the region where minus 3 less than x less than or equal to 0. And then sine of 1 over x, that nasty oscillating thing, if x is positive. And the question says, where does the limit fail to exist? Well, the only place that you have to worry about, because these functions are continuous as long as they exist, like as long as you stay away from 0, even this nasty thing is continuous. So all of these are continuous. The only place you might miss is where you take these functions and sew them together. So at the seams. So you have to worry about negative 3, and you have to worry about 0. Those are the only two places. So you have to check out the limit at each of those places. And to figure out whether the limit exists, you have to ask yourself, what is the limit from the left at each of those places, and what is the limit from the right, and see if they match. Well, if you take the limit from the left of as x approaches negative 3. So x approaches negative 3 from the left side. That means we're in this part. X is less than negative 3. Right? X approaching negative 3 from the negative side. So you have to use this formula. And 2x gets close to what as x gets close to negative 3? Well, that's not hard. Negative 6. Okay, check out the limit now as x approaches negative 3 from the right. That means x is bigger than negative 3, so you're over here. And you've got to use this formula, x minus 3, but this function, f of x, is x minus 3 when x is a little bit bigger than negative 3. So as you get close to negative 3, this becomes close to negative 3 minus 3, which is negative 6 also. So the limit from the left and the limit from the right agree, and therefore the limit as x approaches negative 3, no left or right, is negative 6. So the function does have a limit at negative 3. A lot of you said there's no limit, but what you were confusing, I think, was the fact that there's no y value. F of negative 3 for this function does not exist. Check it out. You can't plug negative 3 in this part, you can't plug negative 3 in this part, so negative 3 falls through the cracks, you might say. There is no y value possible for x equal to negative 3. So negative 3 is not in the domain. You can't plug it in and get a y value out of it. So f of negative 3 does not exist. So the graph of this function so far would look something like this. You'd have a line of slope 2, which is fairly steep, and then you'd have a line of slope 1, and they come together at the same point, but the point is not included. That negative 6, which would be the y value here. The function is getting close to negative 6 from both sides, but it doesn't have a y value at negative 3. So the function is not continuous. It has a hole. By the way, it's a removable discontinuity. Obviously, we could fix that just by defining this function. You could put a less than or equal to here, and that would work. Or a less than or equal to here, that would work. Or you could add another line and say f of x equals minus 6 if x equals negative 3. Any of those ways would fix this and make it a continuous function and give you a y value, which is the way it's supposed to be. But as it stands, the y value does not exist, but that wasn't the question. The function has a limit at negative 3, no problem. So far this function has a limit at every point, but at 0 we're going to run into a problem. And the problem comes in with this side. This is a function that you've had to play with before. You should know it. It's this thing that oscillates more and more and more. And as you get closer to 0, it oscillates even more. So it goes all the way up to 1 and down to negative 1 infinitely many times before it gets to 0. So it does not settle down to any one particular y value. So what that means is the limit as x approaches 0 from the right of sine 1 over x does not exist. So if the limit does not exist, you're done, because the question says, where does the limit not exist? And it can't exist at 0, because from the right, there is no limit. Okay, number 4, you're supposed to find the limit of this rational function, x squared minus 4 over 2x minus 4. And you're supposed to find that limit as x approaches 2. Well, reality check, 2 squared minus 4 is 0, 2 times 2 minus 4 is 0, so you have a 0 over 0, bad news. But this fraction can be factored, so it's x minus 2, x plus 2. And the bottom, you can at least pull a 2 out to see that it's x minus 2 that's left. So of course those two things are going to cancel, and you're really left with x plus 2 over 2. And as x approaches 2, there's no problem with that at all. As x approaches 2, the top goes to 4, the bottom goes to 2, so the answer is 2. Next question, square root of 4 plus x minus 2 over x, and we want the limit of that as x goes to 0. Once again, reality check. As x goes to 0, obviously the bottom goes to 0. The top goes to square root of 4, which is 2, minus 2, that's 0. So we got bad news, as expected. But this is kind of begging for that trick that we talked about many times. You've got a radical, you've got a difference, so you should be multiplying by the conjugate. Multiplying by the conjugate is going to get rid of the radical in the numerator and make good things happen. So we're going to multiply top and bottom by square root of 4 plus x plus 2. So we do it to the top, we do it to the bottom, and that's going to give us an instance of a squared minus b squared. That's why we do it, because we get the difference of two squares. So the radicals go away on top, and you're left with 4 plus x minus 2 times 2, which is 4. And the bottom, don't multiply, just leave it alone. X times square root of 4 plus x plus 2. If you multiplied that out, the very next thing you're going to have to do is factor it back out again to see the x's cancel. So that's obviously a waste of time. 4 plus x minus 4, clearly the 4's go away. You're left with x on the top, so you can cancel the x's, and that leaves you with limit as x goes to 0 of 1 on top, divided by square root of 4 plus x plus 2. And that limit is 1 over 2 plus 2, 1/4. Okay, next problem had to do with absolute value. So we wanted to see what happens as x approaches 2 from both sides of this function. Let's see. Absolute 2 minus x divided by 2 minus x. So what happens to this thing as x approaches 2 from one side or the other? Well, let's try first when x is approaching 2 from the negative side. What that means is that x is less than 2. So if x is less than 2, what does that say about this 2 minus x? In this case, 2 minus x, if x is less than 2, you're taking away from 2 something that's smaller than 2. So 2 minus x has to be a positive number. What does absolute value do to positive numbers? Nothing. Leaves them alone. So in this case, what you're looking at is 2 minus x, because 2 minus x is known to be positive when x is approaching 2 from the left side. So you get 2 minus x over 2 minus x, which of course is 1. All right. What about the other possibility? What happens when x is approaching 2 from the right? Well, that just means that x is bigger than 2. Think of the picture. Here's 2. Where's x? X is over here. So x has to be bigger than 2. So if x is bigger than 2, what's that say about 2 minus x? You're taking something bigger than 2 away from 2, so that makes it negative. Makes 2 minus x negative. So here's the big question. What does absolute value do to 2 minus x? What kind of a number is 2 minus x? It's a negative number. So of course absolute value has to make it positive. How does it make it positive? Absolute value makes things positive not by erasing minuses. It makes things positive that are known to be negative by sticking a minus in front. It just stamps it with that minus. So it gives you the minus of 2 minus x, the opposite of 2 minus x. So if 2 minus x is known to be negative, absolute value sticks a minus in front to make it positive. So the quantity that we were dealing with, absolute 2 minus x over 2 minus x in this case, reduces to just, well, is minus 2 minus x over 2 minus x, because that's what the absolute value will be, and obviously that's negative 1. So the limit from the right is negative 1, and the limit from the left is positive 1. All right. Now you had to use the definition, or use a definition of the derivative to find the equation of the tangent line to the function x minus x squared, that's our f of x, at the point 1, 0. You better make sure, double check that this point really is on the curve. When x is 1, you get 1 minus 1, and that's 0. So yes, 1, 0 is on the graph of x minus x squared. Many of you drew the graph of this because you knew that x minus x squared is a parabola. It opens downwards, and it even factors as x times 1 minus x. So it's clear that the places where the parabola hits the x-axis are at x equals 0 and at x equals 1. So those are the two places where f of x is equal to 0. It's a parabola opening downwards, so the graph has to look like this. It's not bad to do something like that to get some information about what you're dealing with. So that the slope of the tangent, well, the question says what's the equation of the tangent line at 1, 0. So you can see the tangent line is going to look like this. So you better get a negative slope as your answer, or else you did something wrong. Okay, so what's the definition say? Well, you can pick whether you use the x approaches a form or h approaches 0. I think I would rather use the x approaches a form because I'm not interested really in the derivative of f at every point x. I'm interested in it at x equal to 1. So I want f prime at 1, which will be the slope of the tangent line at 1. So by definition, using the definition in this form, limit as x approaches 1 of f of x minus f of a is 1 in this case, divided by x minus 1. Substitute in, you get for f of x, x minus x squared. And now for f of 1, that's very good because we know what f of 1 is. It's going to be 0. Check it out, 1 minus 1 squared. So I don't have to write that. Divided by x minus 1. And of course, we have a 0 over 0 bad news situation. But you can see that that numerator is going to factor. We already factored it. It's the limit x approaches 1 of x 1 minus x divided by x minus 1. Now you have to see that 1 minus x is just like x minus 1 except flipped, reversed. So to spell it out here, this is the same as limit as x approaches 1 of minus x times x minus 1 over x minus 1. I reversed the 1 and the x and it cost me a minus. Right? If you don't believe it, take the minus 1 that's here and distribute it across those two guys, and you get minus x plus 1, which is exactly what we have there. But here now you can see the x minus 1's cancel, and so the limit as x approaches 1 is minus 1, and so that's our m, our slope. And so the equation is y minus the y value here is 0, equals the slope, negative 1, times x minus the x value. And that is good enough. Lots of people wrote that on the test as the equation aligned, and you can see that I did not take a single point off for doing that. It's a perfectly good equation for a line. Okay. This one caused problems for some people, although some people did rather well with this. The question is, if you've got this equation x cubed plus 4 equal to 2x squared plus x, how can you be sure that that has a solution on the interval from negative 2 to 0? Well, this was just like problems that we've had to do with the intermediate value theorem. You just make a function out of the difference between those two sides of the equation. So f of x is x cubed plus 4 minus 2x squared minus x. So I just subtracted the right side and made a function out of this. So now I've transformed the problem of solving this equation into a problem of finding a 0 for this function. Find a place where f of x is equal to 0. Because if I can do that, then that says x cubed plus 4 minus 2x squared minus x is 0 at some point. Then, since it's equal to 0, I can throw these guys to the right and get exactly this equation, and I have found a solution. So I've transformed the problem into one of finding a 0 for that function. Well, how do I do that? Well, the intermediate value theorem says that if I have a continuous function, oh yeah, this is continuous, and I need to say that. F is continuous because it's a polynomial, but on a test, it's good enough to just say f is continuous. Next, you need to check out what f does at these points at negative 2. So if you check out f of negative 2, you get negative 2 cubed plus 4 minus 2 times negative 2 squared minus negative 2, which turns out to be negative 8, plus 4 is negative 4, and then this is minus another 8. So it's negative 4 minus 8 is minus 12, and then plus 2 is minus 10. You can do the arithmetic yourself. F of 0 is easier. You just put 0 in here, 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 and the only thing that's left is 4. So here's the situation. you've got this function that goes from -2 to 0 on the x-axis, while the y values at -2 are down here at -10 and then 4 at 0. How can a continuous function go from -10 to 4? Well, it has to pass through every y value, every single y value in between -10 and 4, including 0. So by the intermediate value theorem, IVT, there must be, or you could say there exists, an x between -2 and 0, such that f of x equals 0. And at that point, whatever that point is, it'll be the place where the function f of x is 0, and that will be a solution to the equation. Okay. That takes care of number 8. Number 9, again, was a problem with limits and continuity that caused some trouble for people. The question says to figure out whether we have continuity from the left and continuity from the right at each of these 3 places. So what I'm going to do is not write the function, but just calculate here. What is the limit as x approaches 2 from the left of this function? Well, if I'm approaching 2 from the left, I'm less than 2, and so I have to use, this is the limit as x approaches 2 from the left, I have to use the formula 2x minus x squared, because that's what part of the formula I'm in, part of the definition of f I'm in. And in that part of the definition, then, I can calculate the limit here. That's going to be 4 minus 16, no, 4 minus 4, that's 0. So the limit from the left is equal to 0. To tell whether this function is continuous from the left, I have to compare that with f of 2. Well, what is f of 2? f of 2, I have to use that same part of the formula to calculate f of 2. So I get 2 times 2 minus 4, which is also 0. So yes, the function value, this is the y value of the function, and the limit of the function match. So yes, continuous from the left. We also have to check from the right. What's the limit as x approaches 2 from the right for this function? Now we're into a different part of the definition, so we have to look at the formula x instead of 2x minus x squared. So this is x approaches 2 from the positive direction of just x. And the answer for that limit is pretty easy. As x goes to 2, x goes to 2, whether you're going from the right or the left. But see, this is the limit from the right. The value of the function is 0, so the limit from the right does not match the value of the function, so it's not continuous from the right. Okay, that takes care of 2. For 3, we do exactly the same thing. Limit as x approaches 3 from the left of this function. I'm not going to write in the function anymore, I'll just calculate it. If I'm looking at 3 from the left, I'm still in this area where I'm dealing with x as my function. So as x approaches 3 from the left, the answer is just going to be 3. What's f of 3? Well, it's the same formula, because this says when x is less than or equal to 3, I have to use x as my formula. So x is 3, so f of 3 is 3. And that matches the limit. So once again, yes, continuous from the left. Check out the limit as x approaches 3 from the right. So if this is approaching 3 from the right, we have to use x bigger than 3, which means we're into the x minus 4 region. So this is the limit as x approaches 3 from the positive of x minus 4. And that limit, of course, is negative 1. And how does that compare with f of 3? Well, we knew f of 3 was 3. That's not negative 1. So it's not continuous from the right. I'm not going to write that, but obviously not continuous from the right. And then finally, the limit as x approaches 4. We have to take that from the left. Limit as x approaches 4 from the left will be, well, we'll be using the formula x approaches 4. Let's see, so that's x less than 4, so we're still in this x minus 4 region. And so the answer is going to be 4 minus 4, or 0. How does that compare with f of 4? Well, when you look at 4 in the domain, you have to use the last formula because that's where it says x greater than or equal to 4. So when x equals 4, you're going to get a value of pi. So pi doesn't match 0, so the limit from the left is not the value of the function, so it's not continuous from the right. How about from the left? If we go from the left, that was left, sorry. Got to go to the right, the other left. So if you go to 4 from the right, we're using the formula pi, because when x is bigger than 4, that's what y is. And so obviously the answer is pi, because it's constant. And that's the same as f of 4, so yes, continuous from the right. Okay. Now we have a couple of limit problems, limits at infinity. So as x approaches infinity, we have to find the limit of 3x squared minus 9x minus 10 over 4x squared plus 9x plus 5. And here, as x gets large, clearly the top and bottom are both going to infinity, so we have an infinity over infinity bad news situation. The trick, you multiply top and bottom by 1 over x to the highest power, so that's 1 over x squared. That, when you distribute it, is going to just give you 3 minus 9 over x minus 10 over x squared divided by 4 plus 9 over x plus 5 over x squared. And the good thing about doing it this way is that now you can see that as x gets large, this thing goes away, this thing goes away, all of these are going to 0, leaving you with just the 3 and the 4. And so this goes to 3/4 as x goes to infinity. Number 11, same kind of problem, almost the same situation, except that the function on the bottom is a little bit more complicated at 9x minus 10. But we've had these kinds of problems before. We've got this square root. In fact, this is much easier than that nasty quiz problem that I gave you that I had to reject. So you got x squared minus 5x plus 9 under the radical. But here x is going to positive infinity, so there's no question about the fact that top and bottom are blowing up. So you're still going to use the same trick of multiplying by 1 over x to the highest power, which is 1 over x to the first. Some people thought it's 1 over x squared. And you can try that. I mean, it's not wrong to multiply top and bottom by 1 over x squared, but what's going to happen is then you're going to end up with a situation, if you did everything right, where both top and bottom go to 0. So you've traded an infinity over infinity for a 0 over 0. It's true, but not helpful. Not helpful. So here you've got to use 1 over x divided by 1 over x. But on the bottom, well, let's do it slowly here. So this is going to give us on the top 9 minus 10 over x. On the bottom, however, how are you going to get this 1 over x underneath the radical? The answer is you got to put it under a radical itself. Well, 1 over x is not equal to the square root of 1 over x, but it is equal to the square root of 1 over x squared. So you take 1 over x, write it as the square root of 1 over x squared, and then distribute this 1 over x squared onto the radical. And that gives you good stuff. That's going to cancel the x squared entirely, leaving you with 1. And then minus 5 over x, and then plus 9 over x squared. Once again, as x gets large, this guy's going to go away, this guy's going to go away, this guy's going to go away, leaving you with something that goes to 9 as x goes to infinity. Okay. Then we had the limit, what should have been a very, very easy problem. Limit as x goes to infinity of sine x. Some of you drew the graph of sine x. Here it is. Looks just like that. Forever and ever and ever. What's that doing as x gets large? Well, it keeps doing that. Does it approach a single number? No. Does it blow up? No. It just keeps going back and forth from -1 to 1. So does it have a limit? Nope. The limit does not exist. End of problem. And finally, we had this thing, the limit as x goes to infinity of 2 to the inverse tangent of x. Well, you had to remember that inverse tangent is one of my favorite functions, and so you need to remember the graph of inverse tangent. The graph of the inverse tangent is asymptotic on both sides and grows to a maximum, well, it never gets there, but it's asymptotic to pi over 2. And on the other end, it's asymptotic to minus pi over 2. But as x gets large, the inverse tangent is going to pi over 2. So look, if this guy, the exponent, is going off to pi over 2, and 2 to that power is going to do what? Well, 2 to a power is a continuous function. So if this guy is going to pi over 2, then 2 to that power has to go to 2 to the pi over 2. And that's it. That's the answer. Now somebody wrote this in a clever way. I didn't see it, but somebody wrote it as the square root of 2 to the pi. And that's true. But this is good enough. All right. Find the horizontal and vertical asymptotes for this function, x squared minus 4 over x squared plus x minus 2. So let's do the horizontal ones first. Horizontal asymptotes are where the limit as x approaches infinity is equal to something. So what happens when x gets large? Where are your horizontal asymptotes? Like here, as x gets large, your horizontal asymptote is pi over 2. As x gets small to negative infinity, you're getting minus pi over 2. What happens here as x gets large? Well, we've been here before. You multiply top and bottom by 1 over x squared. So you're going to be looking at 1 minus 4 over x squared divided by 1 plus 1 over x minus 2 over x squared. And obviously that goes to 1. By the way, it goes to 1 whether you're going to plus infinity or minus infinity, because same trick works. Think about it. When x goes to negative infinity, all of these guys are still getting small. Even this one. X gets negative infinity, 1 over x is going to go to 0. So all these guys go to 0 whether you're going to plus or minus infinity. And so 1 is the limit. And so you're going to have a horizontal asymptote at 1. That is y equals 1. Just like this is y equals pi over 2. For vertical asymptotes, you have to have the limit as x approaches some number a of your function being plus or minus infinity. That's what a vertical asymptote is. Not just having 0 in the denominator. The limit must blow up. So here, if you factor the denominator to look where the zeros are, you're going to get x minus 1, x plus 2. So you would think that means x equals 1 and x equals negative 2 are going to be asymptotes. However, the numerator also factors x minus 2, x plus 2, which means that this x minus x plus 2 is going to cancel, leaving you with x minus 2 over x minus 1. And as x approaches negative 2, there's no problem here. This does not blow up. The graph would look like this. You would have a hole at that point. There's a discontinuity, but it's not a discontinuity where it's blowing up. It's just a removable discontinuity. So this function does not blow up at negative 2. So this is not a vertical asymptote because the limit exists. The limit, it turns out, is, what is it? We're approaching negative 2, so this is negative 2 minus 2 is negative 4 over negative 3. Negative 4/3 is the limit. So there's no problem at that point. It's not, the function is not blowing up. We do not have an asymptote. But we do have one at x equal to 1. So this is our vertical asymptote. Okay, then we come to the last two, which are the limit problems. And the first one asks you to find a delta that works where you're given this function f of x equals 3x minus 2 and the limit being 4. Well, a lot of you did really good things here. You said f of x, which is 3x minus 2, the distance between 3x minus 2 and 4, the distance 4 between f of x and L is supposed to be less than epsilon, and epsilon was 1/2. So you can write that. And then play with it until you get to something that looks like the distance between x and 2 and something. So if you just simplify this, this is going to be 3x minus 6 less than 1/2. Factor out the 3 times x minus 2, absolute value less than 1. That 3 can come out because it's positive. So you've got 3 times absolute x minus 2 less than 1, or, I'm sorry, this is not less than 1, this is less than 1/2. All of those are 1/2. So now you got to divide both sides by 3, and you get absolute x minus 2 less than 1/6. And this is the distance between x and 2. The distance between x and 2 less than 1/6 is mathematically equivalent to what we started with, the distance between f of x and L less than 1/2. So how can we satisfy the boss's requirements of getting within a tolerance of 1/2? We just make our x this close to 2 or closer. So if the distance from x to 2 is less than 1/6, the distance from f of x to L will be within tolerance. So this is our delta. Okay. And the final question, I think just about everybody got that right. If you look at the graph and you see how far you can wander away from the a value, which is 5, how far can you go on either side, that'll be your delta, so that your y values stay within the epsilon strip, which goes between 3.6 and 2.4, which I miscalculated, but that didn't matter. It's just getting it within the epsilon strip. So obviously if you go from 5 all the way back to 4, you're within tolerance on the left. The function will stay within the epsilon strip. But if you went that far on the right, if you went from 5 to 6 on the right, you would be beyond the 5.7 point, and you see the function is increasing, and you'd be above 3.6, which is the most that you're allowed to have for this function. So you can't go that far, so you have to stop at 5.7. So how far can you go on both sides? What is the delta that will work? Well, 0.7. So delta is the best value, the largest that would work. If you got a smaller value for delta than 0.7, that would work, but it's a little bit of overkill. All right, and that's it for the exam, for exam 1.